Hello students, welcome back. In the previous video, we discussed the meaning of the definite integral using the concept of signed area and accumulation. And this was the graphical representation of the definite integral, the signed area. And then we discussed some properties of the definite integral, like these and those. And finally, we discussed some estimation problems using the graphical representation, kind of like this and that. Now, in this lesson, we are going to focus upon precise computation when the algebraic expression of the integrand is known. And the main tool we're going to be using is this one, the fundamental theorem of calculus. As the name suggests, this is very important theorem. In Calculus 1, I usually say this is the second most important theorem, second only after the chain rule. Chain rule is the number one. Now, if you put together not just Calc 1, but Calc 1, 2, 3, Advanced Calculus, Real Analysis, everything put together, then the fundamental theorem of calculus becomes number one. It goes like this. We begin with a continuous real function, small f of x, defined in a closed and bounded interval a to b, and this theorem has three parts. The definite integral exists. You see, in order to have any kind of computation, this should exist. Number two, an antiderivative exists. Finally, we can calculate the definite integral which exists using the antiderivative which exists. And the definite integral is the net change of the antiderivative, capital F of b minus capital F of a. Now, let's talk about how to use this. And let's go to some elementary integral problems here. And this is a nice problem, so let's go with this. Now, let's do this in a little bit stupid way first, and then we're going to discuss a little bit more clever way. A stupid way first. Instead of calculating the definite integral directly, let's find out the indefinite integral or the antiderivative first. So how does this thing work? Well, break up the parentheses inside using the FOIL method. First, outside, inside, and finally last. Is everything okay? And then we take the antiderivative to t plus 1/3 t cubed minus t squared minus 1/4 t to the 4th power plus integral constant c. That's the antiderivative in general form. There are infinitely many of them because the c value can be anything. Now, using this, let's find out the definite integral. This is equivalent to capital F of b minus capital F of a. Excuse me. Capital F of b minus capital F. I keep mistyping, sorry about that. That's because I'm speaking and typing at the same time. Sorry about that. Okay, alright. Let's do this computation. And looks like I'm gonna need a little bit more space, so let's go down. Okay, let's put t equals to 1 to this expression and t equals to 0 to this expression. Alright, plugging t equals to 1. T equals to 1, and then t equals to 1. Now, t equals to 0 this time. T equals to 0. and then t equals to 0, and then t equals to 0. Okay, that looks good. So let's finish this computation. Now, please note that plus c and plus c will cancel each other out. And then what's left will be 2 plus 1/3 minus 1 minus 1/4, and then all these are zeros. So that's going to be our answer. And let's simplify all that. Let's see. 1 plus 4/12 minus 3/12. So this is 12 over 12. So everything is 13 over 12. I guess this is correct computation, but I do not trust my mental math entirely, so I'll use Mathematica to confirm that. Yes, that's correct. Anyway, this is a computation, but in my opinion, it's a little bit stupid. It is done in two parts. Number one, the antiderivative computation, and then plugging the top and plugging the bottom, subtracting one from the other. Yes, it's correct, but overly complicated. So I'll do it in a little bit more clever fashion like this. Let's see. Excuse me. Let's just copy this. And then, okay. Okay, don't pay attention to the second line yet, and then look at the first line. Just worked out the integrand as if you're taking the antiderivative, except that the integral from 0 to 1 stays as before. And then let's go over to the second step. Let's take the antiderivative. Well, we already did it over here, so let's go ahead and do that. But two things. Number one, plus c do not play any role, as we saw before. This plus c down here, plus c there, will cancel each other out, so we just get those off. And then I have to take care of this notation, integral from 0 to 1. How do I do that? We do it like this. From the bracket, I put 0 to 1. And what does it mean? It's a shorthand that I'm going to plug in the top, t equals to 1, and then plug in the bottom, t equals to 0, to this expression, and then subtract one from the other, which is coming down right here. So plug it on top, and then plug in the bottom, except that of course I'm not using plus c anymore, so let's get those off. And okay, here's a computation completely. So both of these two together in a single step, and this is a little bit more clever way that I'm going to use all the time. Our textbook author does the same thing. Just like the indefinite integral or antiderivative computation, manipulate the integrand and find out the antiderivative, except that we use this bracket notation. This bracket open and then bracket close with, okay, I'm having a little bit difficulty getting appropriate highlighting. And this part, t is going from 0 to 1, and then that means plug in t equals to 1 and t equals to 0, subtract one from the other. Now, sometimes this can be a little confusing, especially when there are more than one characters. For example, there is some parameter a or b flying around. In that case, which number do I plug in is a little bit unclear. In that case, we do like this. T is going from 0 to t equals to 1. That means we are plugging in t is equal to 0 and t is equal to 1. Some people scrutinize this one even further and then use arrow notation here instead of equality there. Now this is probably the most standard and also complete expression. Plug in t as 0, plug in t as 1, but then again most of the time you have just only one character, so you don't have to worry too much about this specifying this character. But maybe it's a good idea to recall all these, because in the next module we're going to deal with integration by substitution, where we have to deal with more than one characters. Anyway, in that case maybe we'd better bring those back. Okay, do we have enough time? Okay, whether we have enough time or not, let's do just a little bit more exercise. This time we're going to go over to the clever method directly. Okay, so just like before, we're calculating the antiderivative, and the denominator, change it into power form. That's a little bit more convenient. And then let's manipulate the integrand. 3x divided by x to the 1/2 power minus 2 divided by x to the 1/2 power. We have done these before. It's just manipulation of the integrand. The next step, we have to get appropriate powers. So okay, x to the first power divided by x to the 1/2 power. 1 minus 1/2, so we get positive 1/2 power. And here you're gonna get negative 1/2 power. We have done this before, so I'm moving a little bit more quickly than we had done before. Okay, let's calculate the antiderivative. 3 is the coefficient, so it stays there. Add 1 to the power, and then we have to divide. That's the essence of the power rule. Okay, 2 times x to the, add 1 to the power, so 1/2 power, and then divide, reciprocal. And then x is going from 1 to 9. X is moving from 1 to 9. And let's plug in 9 and let's plug in 1 and subtract 1 from the other. So let's plug in 9 here. Nine to the 3/2 power. By the way, 3 times 2/3 simplify into 2, and this one simplify into 4, and then plug in 9 over here. All right, subtracting top minus bottom. Okay, this time we are plugging in x equals to 1, so instead of 9 we have to replace those with 1s here. So if we calculate, what do we get? Is this something that I can calculate easily? Let's see. 9 to the 1/2 power is square root of 9, that's 3. 3 to the 3rd power is 27. So this is 2 times 27, that's 54. And then 4 times 3, that's 12. And then 2 times 1 and 4 times 1. So what do we have? 54 minus 12, that's 42, plus 2, you're gonna get 44. I don't trust my mental math, so I'll use calculator to figure it out. Here we have Mathematica $1,000 calculator. So here we go. Yes, 44 is correct. Now, do I have enough time for this problem? Okay, I'll try. Okay, what is cosine squared? What is cosine squared? Come on, okay. It is 1 plus cosine of 2x divided by 2. That's the power reduction formula, or some people call it half angle formula. For the purpose of the antiderivative computation, however, it is more convenient to separate the numerator like this. 1/2 plus 1/2 times cosine of 2x like this. Oops. Okay, let's calculate the antiderivative. Antiderivative of 1/2 is 1/2 x, and then 1/2 was there before, and calculate the antiderivative. Cosine becomes sine, and then you have to divide by extra 2. So we need another 1/2 there. And then we have to plug in 0 to pi. Oops, what did I click? Okay. Alright. Plugging in pi, what you get? Pi over 2 plus 1/4 sine of 2 pi. But sine of 2 pi is 0. This whole thing is going to become 0 minus plugging in 0. Oh, that's even easier. X equal to 0, so this is 0 over 2, that's 0. And then we have sine of 0 here, that 2 is 0. So what do we get? We get pi over 2 plus 0 minus 0, another plus 0, all gone, and that's going to be the final answer here. So how do you calculate the definite integral? Well, just calculate the antiderivative here, just the antiderivative computation up to this line, and then remember this bracket notation so that plug in the top and plug in the bottom, subtract from the other. With the help of calculator, you can easily get it done. Same thing over here, up to the third line, it's the same as the indefinite integral computation. Plug in 9, plug in 1, subtract from the other, and then you can use calculator. Here I didn't have calculator with me, so I just used my mental math, but you don't have to. The same thing goes on here. Up to this point, it's just the same as the antiderivative computation. Plug in the top, plug in the bottom, subtract from the other. As far as the notation is concerned, this integral from a to b dt gives rise to bracket open, bracket close of this top and bottom, and then plug in the top and plug in the bottom, subtract from the other. And that's how this definite integral computation works.